Good evening, everyone. Wonderful to see you all here for this March Research Tuesdays Forum, Machines Rising. Can I first acknowledge the Kaurna people, the original custodians of the Adelaide Plains and the land upon which the University of Adelaide's campuses at North Terrace, Waite and Roseworthy are built. I'm Mike Brooks, I'm the Deputy Vice-Chancellor of Research here at the University of Adelaide, and it's wonderful to see you all here. To say our subject this evening, machine learning or AI, artificial intelligence, is a hot topic right now would be a real understatement. And to put that in perspective, all 500 plus seats at this presentation were booked out several weeks ago before any of our usual event promotion had taken place. It's obviously an area of rapid technological development that already affects our lives in countless ways. AI is accelerating progress and development in fields as varied as medicine, agriculture, defence and transport. It can be expected to have a major impact, of course, on jobs and society. It's interesting in the news today, almost preliminary to our event, that Mike Cannon-Brookes, not to be confused with Mike Brooks, he is the 499th richest person in the world, I gather, who heads up Australia's biggest technological company, Atlassian. He's today warned of the social cost of failing to plan for technological disruption. The University of Adelaide is very much at the forefront of AI research and development, and this was recognised by the South Australian government late last year when it co-invested in the establishment of our new Australian Institute for Machine Learning, launched in December. Tonight you're going to hear from some of our leading researchers as we consider machine learning and AI from multiple perspectives. Its benefits, recent and coming advances, and some of the potentially unwanted impacts that society will need to consider. Our presenters this evening are Professor Anton van den Hengel, Director of the Australian Institute for Machine Learning, Dr. Fiona Kerr, Industry Professor, Neural and Systems Complexity, Associate Professor Jeremy Woolley, who directs the University's Centre for Automotive Safety Research, and Professor Ian Reid, Australian Laureate Fellow, Deputy Director of the Australian Research Council Centre for Excellence in Robotic Vision. Each will present individually on their respective fields of expertise and current work. All four will then participate in a panel discussion in which they'll delve deeper into the topic and take questions from the floor. So we encourage you to get involved, of course, at that point. So without further ado, it's my great pleasure to introduce Professor Anton van den Hengel. As I mentioned earlier, Anton heads our new Australian Institute for Machine Learning. His research has led to over 250 publications, 9 commercialised patents, and attracted more than $20 million in external funding. Anton, welcome.
Thank you very much. I'm Anton van den Hengel. I'm the Director of the Australian Institute for Machine Learning, a Professor of Computer Science in the School of Computer Science at the University of Adelaide, and Chief Investigator on the Australian Centre for Robotic Vision and ARC Centre of Excellence. Thanks for coming. And thanks for making it so popular. Amazing response from people. There's obviously a lot of enthusiasm. I think that one of the questions, I hope that one of the burning questions that you've come with today is, what is machine learning? And particularly I think there's a lack of information, there's a bit of fear, and then there's some confusion about how it relates to artificial intelligence, big data, a bunch of these terms that have been pushed around the media a lot, and there's a lot of, well, fear-mongering as well as a lot of enthusiasm, and probably a little bit too much of both. So maybe we could start out by trying to figure out what machine learning actually is. So if you're going to program a computer, you're going to try to convince a computer to do absolutely anything, then you need to give it a set of instructions. Those instructions have to come from somewhere. The traditional way that you try to get a computer to do what you want it to do is that you write code. And so code is a bunch of lines in a text file that look a lot like this. And so a human being comes up with a recipe, right? An algorithm for how they'd like this computer to do the job that they imagine it doing. That served us very well as a way of getting computers to do what we want them to do. It's a large part of what drives your phone and the 20 computers that are already in your car and the one that's in your microwave and all of the computers that are around you. It does have a few limitations, however. One of the limitations is that a human has to be able to describe to you how they want that job done. And there are a whole lot of jobs that humans do that they can't describe, right? You can't describe to somebody how in any meaningful way, how to walk, how to talk, how to do any of the things that we take for granted, right? So if, for instance, you wanted to try to convince your computer to be able to distinguish between images of cats and images of dogs, then the traditional way would be that you try to write code which can distinguish between those two classes of images. So an image to a computer is just a rectangular array of numbers, and you'd have to come up with a recipe for distinguishing images of cats and images of dogs. They're a particularly broad class, right? Dogs particularly don't have all that much in common. And most of what you could say that they have in common, they also have in common with cats, right? You can't look for brown furry things or things running, or you can't even distinguish them on size, right? They both exist at all sorts of size ranges. There really isn't a good recipe for how to distinguish between a cat and a dog, or images of cats and dogs. The machine learning process is that you don't try to come up with a recipe for how to distinguish images of cats from dogs, but you rather come up with a recipe for how to allow the system to learn from a set of examples how to make that distinction itself. Right? So what we do in machine learning is to try to come up with more and more clever ways of giving the machine the capacity to learn from these sets of examples. And it's a lot like the way that humans learn, right? Humans learn by example. Humans have a whole lot of experiences in their life, and they learn to make those kinds of distinctions. So, and really the methods are incredibly complicated. It's very mathematical. It's a wonderful field. If you're looking for a career, I can recommend it highly. It's not only incredibly interesting, it's very well remunerated if you do go to the private sector. It's doing amazing things. But the simplest way to think about it, the simplest way that you could think about how to achieve this incredible result of learning to distinguish images of cats from images of dogs, for instance, or this one, these are handwritten digits. It was a very important practical problem 20 years ago. The US Postal Service created a huge data set of handwritten digits in order to allow a machine to be able to read these digits automatically, to be able to read postcodes, of course. So the simplest way that you can think of achieving this amazing feat of machine learning is just nearest neighbor. So each one of those things is actually an image. In this particular data, I can't remember the exact image size, but it's not all that big. It's only 10 by 10 or 16 by 16, something like that. And if you have this huge data set of numbers, so you take your data set of 60,000 numbers, and somebody gives you a new image. Now, to the computer, the image is just a set of bright and dark patches, right? It has no idea of strokes or fourness or sevenness or any of that sort of thing. It's just a picture. And the way that you can turn that into a 4 is just to match this query image against every one of your database images and pick the closest one. Yeah, so if you pick the closest one and the closest one turns out to be a 4, then you've got a method of turning this image into the number 4. Right? And a really simple to understand, very powerful way to achieve that to achieve that process. And it's even, one of the things that people say to PhD students is you should try nearest neighbour first, because at least it gives you an idea of where the difficulty really lies. So that's, so now you're all experts in machine learning, right? You can go out and participate in the revolution, right? I understand nearest neighbour, I can process postal digits and distinguish images of cats from dogs. The only other piece of information that you need is the relationship between AI, machine learning, and deep learning. This is a slide from NVIDIA, but artificial intelligence has been around for a long time, since the 60s at least, and you've kind of got an idea about what it's about, right? It's about trying to come up with something that that's capable of doing things that we consider to be intelligent. It's a really terrible name for a field, because intelligence isn't defined and artificial isn't really all that well defined either, but you've got an idea about what that means. Machine learning is a subset of artificial intelligence, or one slice of machine learning is as a subset of artificial intelligence. Machine learning is particularly focused on what's currently the more achievable end of that problem. So and particularly what gets called, specific AI, right? It's where we're trying to solve a specific problem, rather than the more hardcore problem, the general AI problem, which is, what will lead you to have a sensible conversation with this thing that is capable of abstract thought. Machine learning's right over in the other corner, trying to distinguish images of cats from images of dogs. And machine learning is one of the technologies that's really made the difference in machine learning over the last, almost decade now. Deep learning is based on neural networks, and there's some relationship between the neural networks that are used in deep learning and the neural networks that are in animal brains, including ours. It's not a very strong relationship. There's more differences than similarities, but there are certainly some similarities. What the revolution in deep learning has been that it's capable of carrying out a whole lot of recognition and regression and classification tasks better than humans. So one of the first ones to go was the German road sign database. Road signs are made explicitly to be identifiable by humans, but one of the breakthroughs was when the machines got better, and deep learning got better at recognizing road signs. And now at most of those classification tasks, cats from dogs, numbers, all of those things, the machines are better than the humans. What machine learning isn't cybersecurity. Cybersecurity is an issue. So cybersecurity is this problem that every now and again a million passwords get leaked, or half of the world's dates of birth get stolen. Cybersecurity isn't machine learning. Machine learning uses a lot of data. It's certainly an issue in cybersecurity is an issue for machine learning, but they're two relatively orthogonal problems. And if you can have, the same problem apply to a bunch of files in a filing cabinet, then it's certainly not exclusive. The security problem is not exclusive to machine learning. Machine learning's not watching you. Machine learning doesn't care. Machine learning's not smart enough to care. It might be smart enough that somebody else could use it to find you on the basis of something they care about, but that's true of so many other things, right? It's always the human. It's a tool. Machine learning is a tool, and the question is, what does the human want to use it for? And particularly, there has been some, made a lot of news a while ago, this idea that Microsoft's image recognition API was racist. I think one interpretation of the result was that it was racist. The truth is, the machine learning was given a task to do, and it did that task as well as was possible. But the data that it was given to learn from had, was not distributed in the way that people would like it. There weren't enough examples of other classes that to give it the information that it needed. So if you spend long enough playing with the interface, you can get it to do something that looks like it's racist. Of course, it's not capable. It's not smart enough. It just doesn't have the IQ required to be able to do that. Okay, and machine learning isn't coming to get you. There are certainly some very smart people who think that we stand an existential threat from AI or machine learning. Elon Musk is amongst them. Elon Musk also thinks that he's going to live forever and that much of that lifespan is going to be spent on Mars. So I'm not sure that he's the first person to be asking. Stephen Hawking is obviously a very bright bloke. And technically, the development of full artificial intelligence could spell the end of the human race, but is incredibly unlikely to, and I don't think that any of us are going to see it. So there is no existential threat from that, I'm afraid. So yeah, I run the Australian Centre for Australian Institute for Machine Learning. We are located at Adelaide Uni. We're one of the best groups in the world, and on a bunch of fronts. We do very well at the pure research. We also do very well at research translation. And we have a bunch of things that we're the best in the world at, and we are particularly, currently working on a bunch of things that people probably don't think of as machine learning problems. We're working on carbon counting for Indigenous communities. We're trying to feed the world past peak human. Or, we're working with biologists to try to feed the world past peak human. We're working on at least 4 intelligent medical devices at the moment, and trying to find some solutions for next generation mining. So I have the advantage of being both MC and a speaker, which means that I've probably already talked too long. But the next speaker is Fiona Kerr. She's an industry professor in neural systems complexity here at the university, and particularly works on the human impacts of technologisation, which is a word I had to practice saying quite a lot. She's working in questions about how technology shapes us and how we shape technology. Fantastic stuff at the intersection between this technology and us, the users of this stuff. Fiona.
I should be turned on. Right, I'm a bit smaller and I'm mic'd up, so I'll stand in the middle. Okay, so, I think I flipped to the next one. So one of the things that I wanted to pick up and go straight on then with from Anton's was we talk about AI isn't racist, but if human wants to use it that way, then we potentially can go that way. So what I want to do today is to, just for this few minutes, to talk about the human aspect of what we think about to do with machine learning in all sorts of different ways. So some of the questions that I deal with. So I work at Adelaide University, and I also work from the faculty of professions into engineering on various things that we look at, including some of the trusted autonomous systems kind of information, that kind of question around, a number of decisions that have to be made, and into health sciences. So I've just finished a 2-year study on the neurophysiological impact of touch and eye gaze on healing and trust, and that's the whole discussion around the robot nurse. When do you use a real nurse? When do you use a robot nurse? How does it affect people in their whole kind of neurophysiology? And also that is very relevant when it comes to a number of questions around us interfacing directly with technology. So one of the first things, if we go back to one of Anton's points, is the neutrality of technology. So technology is neutral, as we know. There's a couple of things that loop back in, and they're very human aspects of that. So the couple of caveats are, one of the things is that technology tends to favour those that, or advantage those that control it or create it. And that's because we write what it does. So it's fairly easy to think about it that way. And the other thing is that technology can be designed to bring out basically the best or the worst in humans to an extent. Because we are fickle things and we interact really interestingly and differently depending on how we feel, what we do, all sorts of things. You know, it's very difficult to actually dictate how we're going to interact or deal with anything. And a really good example of that was Tay. So I don't know, has anybody heard of Tay, the Microsoft chatbot that kind of went rogue within 24 hours? It's the normal kind of example that's given in this sort of discussion. So the 1 minute I guess, history of Tay is it was based on a Chinese chatbot which worked with Chinese teenagers, and it's still going. Very popular. She has her own show. She actually does the weather, go figure. And then Microsoft said, well, that's really interesting. We'll have a chatbot for teenage girls. A couple of things, well, many things were changed, but a couple of the big learnings that came out of Tay going a bit strange and being taken down within 24 hours was the boundary of what the chatbot would use in terms of where it got its information and how it learned about what we did was slightly shifted. It was a bit bigger and also included some of the social networking stuff. Well, we're not very nice on social networks. So the other aspect of it was people. So the humans decided to corrupt it. So they did. And that becomes one of the really big issues when we interact with technology. The more fancy technology gets, the more complex technology gets, the more we're going to have emergent behaviour. So what that basically means is unintended consequences around not quite knowing and not being able to predict what people are going to do in terms of interacting with that technology. So that's one of the main reasons that we need to actually try and understand humans as well. So my PhD covered systems engineering and cognitive neuroscience, and it was a beautiful combination, because what it let me do was look at human neural networks and artificial neural networks, and it was a really fascinating kind of combination in all sorts of ways. So I spend a lot of time talking to really interesting people. When I talk to people about, or especially technologists, about understanding humans, a lot of the interest is around learning from how the human brain works, because we do really fantastic things. Our brain is colossally good at a number of things. We have sort of 5 quadrillion parallel processes. We do all sorts of things that AI can't do. So we have things like elegant degradation, where we can cut out neurons and we still work really well, where that's not possible in an artificial network. Plasticity, we're trying to figure out how exactly we stratify and keep memory. Upgrading, we're really good at just kind of updating as we run along. So there's all sorts of things that if we could find out how we do it, we could increase all sorts of efficiency to do with how we build neural networks. But the other aspects, there's also a brand new area actually of robot epigenetics. And that's doing some really interesting work around not just letting AI and robots, evolve by having a very specific goal and an optimizer, and they would try and get the best result out of it, but also actually allowing them to play around a bit epigenetically and they use the word mate in different ways to come up with very different kinds of combinations of what they're going to do. And what they find is that when you have physical robots that are allowed to make different types of combinations that aren't necessarily just to optimise a behaviour, they actually quite often pick suboptimal ones, like we do. So that sort of thing becomes really interesting, what's happening there and what does it mean? But there's some other reasons which are much more the other way. We're understanding how humans think in order to best use technology and to partner with technology that become really important. So I've picked a few to talk about quickly today. One is that the evolution of technology is actually quite an iterative process. So we also change technology as it changes us. And some of my work is around how technology changes us as we go on. And there's some fabulous, very interesting neurophysiological changes that we make the more we interact with different types of technology. And in fact, we are, I know it's not very romantic, but I think of us as electrochemical bags. And so the more immersive and the more highly complex that technology is, and especially the electrical aspects of that technology, the more comfortable our brains are plastically with actually interacting with it. So it creates all sorts of very interesting processes when we interact with it. We also need to understand the neurophysiological impacts of interaction, whether we are interacting with other humans. So that's a picture of the way that we can now scan the physical synchronization between human beings when you interact. So we have lots of things happening. We have a number of networks in the brain that synchronize, and the more we know the person, the faster they synchronize. The lead time kind of minimizes. It's why if you've been with each other for ages, then you will tend to almost feel like you know what other people are going to say, and it's because you don't have that lag time. We synchronize chemicals because when in looking at each other and spending time, we resonate, we give out theta, we do all sorts of things in a physical space with other human beings. And some of the work in Finland that we do is around your brain acting differently over a screen when you look at someone as a picture, compared to looking at them face to face. So there's really interesting aspects around that. Will that always be the case? Is it the richness of data? Is it only in certain circumstances? When is that a problem? When is it not a problem? Does it change the way we make decisions? Sometimes. And we have all sorts of quirks around what we're comfortable with interacting with. So we're quite happy to interact with a service robot if it's doing something. But in that example, in the experiments, the people were much happier as long as the robot didn't try to talk. When it tried to speak, then they didn't like it. And they certainly didn't like it when we made it look nearly human. So. And there's all sorts of new work as well around that whole kind of feeling of when you get close to looking human, you feel even worse. It gets much more complex the more we unpick it. So that's one side of interacting, but there's some other issues that come into there, and they're around engaging empathy. So when you engage with other human beings, you actually engage empathic decision making, and you change the way you decide various types of things. So one of the things that we have to get better at is figuring out when is that important and when is it not. So if you're in a situation where potentially you're going to have to make a complex decision in a dynamic situation under stress, how does that change the way that you interact with technology or humans, what you take in the way of information from them? And that's some of the work that is potentially what we're going to be doing. So what we're trying to figure out is, what do we need to know about human beings, and what do we need to know about AI and machine learning so that we can make quality partnerships? Because it's very easy to make quantity partnerships where you just want to churn out or digitize things and sort of chop up roles. But is that the future that we want? So how do we actually make decisions around the best use of both? Because sometimes in my work, it's really interesting that humans are actually more effective and efficient in some circumstances. And then there's other times when technology is much more effective or efficient. And then there's sometimes when it doesn't matter, it's neutral. So we have to get much smarter about figuring out what each type of resource brings to any particular problem or issue. So this is an example of a quality partnership. You have a surgeon with probably Google Glass. They're doing something, they're operating and something awry happens. What they're able to do is say, give me the best option here. And very quickly, because of the capacity of AI for aggregation, pattern making, they can get the 3 best solutions, but they make the decision, because they have this beautifully chunked up intuitive knowledge and experience that they bring to that situation, but they also have fantastic cutting edge latest research combined really quickly. And that's the sort of thing that we need to really hone in on. When we do that, when we use AI and machine learning for those positive, interesting goals and questions, we have fabulous outcomes. So we need to make sure it's an enabler, and we need to take advantage, as I said, of the strengths of both. We're often the problem because we confuse ourselves and each other. Excuse me. So we do things like anthropomorphization. Excuse me. And that's an issue that we're delving into a lot, the more that we have robots helping people. So is liking your robot the same as when you used to like your old car? Is that the same as empathy? It doesn't mean that you would like the robot to be with you when you die instead of a human. I haven't yet met someone who said yes, but there's all sorts of things that start to come into that kind of way that we get fond of, all sorts of things. And so what does that actually mean? We often confuse empathy versus emotion. So I've been looking at what exactly happens under virtual reality. And yes, it's extremely immersive, but to call it the empathy machine and to say that when we're in a situation where we can look at something like a camp and then we can completely understand it is of course erroneous, and most people don't even go there, and certainly technologists don't claim that. But we need to be careful because often marketers will. So we need to get much cleverer about how you use what. And then there's our own heuristics. So Anton was talking about how you shape and bound an algorithm that might end up to have, say, racist tendencies because of what it's choosing. So we have our own heuristics, which means that we tend to pick what we think is relevant, and quite often we can be wrong. We can be skewed ourselves. So the last thing I'll leave you with is one of the things that I'm getting involved in is having to really understand what humans do in terms of how they think and how we act, and internal agency, all sorts of things around us, so that we can ensure that the AI we are actually shaping will give us the future that we want. So the work in Finland, and now in America as well, is around trying to think about how you shape moral algorithms for that sort of Stephen Hawking next stage, general artificial intelligence, where it will have a lot more sort of self-agency. Because one group is shaping what is going to actually be quite a controller in some ways of what we do, on the basis of humans being inconsistent, because it's right that the algorithms are getting very, very fancy. We can build in the capacity to try and predict the inconsistency or the unpredictability of humans. And I argue that we're not inconsistent, we're unpredictable. And it's a totally different basis on which to shape the kinds of rules and outcomes that we should be expected to show in terms of how we act in the world. So we need to really be very, very cluey about how we work so that we can figure out how to create those boundaries and rules around how we're going to have to work once we get more and more, I guess, interaction with cleverer and cleverer machine learning and artificial intelligence. Thank you.
Okay, thank you. So the next speaker is Associate Professor Jeremy Woolley. He is the Director of the Centre for Automotive Safety Research here, and will tell us about one of the specific applications of machine learning technology that's likely to impact us in the near future.
Thank you, Anton. Here we are. We're at a seminar on AI, and I didn't turn the microphone on. Okay, so look, what I'll be talking to you today is about the potential of autonomous vehicles, and what's interesting is a system. It's a road transport system that's out there, and what's very interesting, hearing the words from the previous speaker, is things like unintended consequences. Well, I'm sure if I came to you with a blank slate today and said, have I got a proposition for you? I've got this fantastic mode of transport that'll improve the lot of society. You know, it will transport goods and people around the place, build economies, build the structure and the fabric of our society. There is a slight snag, though, in that we'll pay an awful price for it. We'll kill, nationally, 1,200 people per year. In this state alone, we kill about 80 to over 100 people annually, and more than 600 people are seriously injured. The problem is, think of that toll over the decades. And road transport is one of those few systems where we kill and maim people in far greater numbers than you'll ever see in any other system of operation. In fact, if you add up all the deaths from wars and terrorist acts and plagues and various things, deaths from road crashes is right up there. And the annoying thing is it's within our control. It's a byproduct of a system we've got very wrong. So I think we need to look at the potential to minimise the impacts of this on society. And what latest thinking in this area is going to is basically towards zero. And I need to be clear that there actually, morally, ethically or otherwise, can be no other vision but a vision of zero deaths from the use of our road system. Now, part of this is really about having an elimination agenda. We need to eliminate the harm that's being done. Now, this thinking in road safety is growing, and it has been with us for probably 20 years or since the 90s in parts of Europe. But one of the key challenges there is it's not tangible. We throw numbers about, tens of thousands of people killed or seriously injured. We can't feel that. That's just too abstract for us to appreciate and understand. But what we might get with AI and the new automated technologies that are coming out is making this vision more tangible, making it real so that we can actually touch it. And we can see a trajectory in the future where we could increasingly operate a road transport system increasingly free of death and serious injury. The other thing about unintended consequences that we have is this notion of victim blaming. So essentially the road system is a legacy we have where engineers pretty much set up a very efficient transportation system. But basically we had very little understanding of the human factors issues involved. So fundamentally my main argument would be that with the modern road transport system we place people in situations where we can expect them to fail. If you think about various circumstances, put up your hands if you've had a near miss, if you've had a look but did not see incident, or where you pulled out in front of one cyclist and said, whoops, sorry, didn't see you there. These are all failings of designing the system to cater for human factors issues, and we need to look at ways of overcoming that. But simply blaming the users of the system, the road users themselves, is not good enough. And we as system designers certainly have a duty of care and a role to play in changing that picture. So here we can see some examples of the collisions we've been to. We've got a research centre within the faculty of ECMS, and we've been going out to crashes for an awfully long time. In fact, I might say we've been going out to crashes since the 60s. And one of the things I note, I can pull a sample of crashes from the 60s, the 70s, the 80s, the 90s, every decade. And fundamentally, the core crash types and the key injury mechanisms remain constant. We have largely failed over the decades to eliminate the harm being done by these sort of crashes. And if you think of intersection crashes or road departure crashes, the injury mechanisms are still by and large the same. And the problem is we have too much energy in the system, and the energy in the system, the translation of that energy during the crash is such that death and injury is almost certain to occur. And we've failed to negotiate that, we've failed to tackle that over the years. Now, one of the important things we need in moving forward is understanding incidents. And I don't only say crashes, I say incidents, because near misses and things that didn't go as predicted or planned are important parts of the picture as well. I think it's unfortunate in this day and age when we look at road crashes, because there's so many crashes out there, if we look at the deployment of resources, we only look at those crashes which cause the death or injury, and we don't look at near misses or incidents as they do in other modes of transport. But what will be interesting as autonomous vehicles and driver assist systems become increasingly prevalent is understanding what's behind an incident, what's behind a crash, how did the harm result, or how did the near miss result. And often we're not going to have the answers. We're going to have this AI contributing to the performance of the vehicle, and it may be assisting the driver or doing the job for the driver altogether. Understanding what happens with these interactions and what went wrong is going to prove very challenging. And certainly one of the biggest challenges for us in the future is arming ourselves with knowledge and the capacity to investigate, research and understand what's going on out there in that complex world we're operating. Now, vehicles are becoming increasingly self-aware of things. We have a multitude of sensors that are now fitted to vehicles. The modern vehicle on the market has many, many computers and many, many sensors which provide feedback and assist the driver with the driving task. But the big opportunity in the next 30 years isn't full automation and hands-off and reading the newspaper while you're at the wheel. The big potential benefit over the next 30 years will be the driver assist systems that come in. And indeed, on the market today, we've got many such systems that are in place. We have sensors that cover off when we park a vehicle. You can press a button now and the car will automatically park itself. You have sensors that help you from departing the lane you're in, or brake the car on your behalf in an emergency situation. So all these are already here now with us. And we had mentioned earlier about the need to prepare for the future and make the most of this opportunity. But agility is not within our blood. If you map out the ways we've responded to a lot of these fast emerging technologies, we are nowhere near in a position to optimise the benefits from such things. Now, the nature of the tech fleet penetration over time, here we have a few technologies we can nominate. So here we have ABS, which fundamentally controls the braking of the vehicle, so make sure your car doesn't skid, but instead the tyres keep turning, which means you have directional control while applying the braking. So that's been a feature which has been with us for a long time, but we can see that it's taken about a decade for it to ramp up to quite high levels of penetration in the fleet. We have things like traction control, which also prevent the wheels from spinning when you apply power. Again, we can see it wallowing around and suddenly it takes off and we get good penetration in the vehicle fleet there. Then we have other things like electronic brake distribution, which makes sure we're using all 4 tyres of a car to assist with the braking rather than the front and back pairs of tyres. We have things like brake assist, which make sure we apply maximum braking in an emergency situation in case the driver doesn't press the brake pedal down far enough. And then we have electronic stability control. So again, we can see sort of a slow take-up, then it builds up, and we get to a certain level of penetration over time. But the key thing from this is that look at the timeframes involved here. Generally, a decade before we ramp them up to some level of penetration in the vehicle fleet. And one of the things we know is that the vehicle fleet is has a 10-year average age of the vehicle. You're looking at a 20-year time frame to turn over that fleet. So even if we had the best technology available in a car tomorrow, under the current regime, it's going to take about 20 years before everyone has one. So that's certainly one of the challenges we're working with. And what will be fascinating to see is how society and the community in general embraces these new type of technologies and see if we can accelerate those sort of take-up curves. But if we follow the current model, the paradigm of regulation and some of the non-regulatory levers, there's a very long lag before we realise the full benefits of these things. So we need to think about agility and how we can make the most of the situation moving forward. If we look at the effect of new technologies and crash risk, and this is some modelling we did, just looking at the active technologies. So traditionally our approach to road safety was around passive technologies, passive safety, and that is we let the car protect us, we let the crash occur, and then we see what we can do about mitigating the consequences. With the active technologies, we can now avoid the crash altogether. We can anticipate that something's going to happen and avoid it altogether. We have differentiating implementations of the same capability as well. So on the top, this shows an example of a Volvo, and basically what we're seeing is time to the application of autonomous emergency braking. What the Volvo vehicle does is it provides a warning to the driver at 2.3 seconds out from the collision, and then at 0.9 seconds it applies maximum braking. With the Audi in this particular implementation, it provides some initial braking and stages the car down with some braking. But what's interesting is for the same implementation, the speed reduction in the Volvo is 20k, the Audi is 32k. You will get a variation in performance of these technologies. You'll get different interpretations of these same capabilities with these technologies. So knowing how this will manifest across the fleet and the population will certainly be a challenging thing and something that needs attention in the future. Here we've got quite a complex curve, but basically it's showing a range of crash types showing where the proximity of the striking vehicle will be relative to the bullet vehicle here at 0.0. And this grey band basically replicates the vehicle's vision looking forward. So basically what the vehicle can do is assess who's within this grey band, and therefore is that a dangerous situation? Do I need to brake? Do I need to act on behalf of the driver? This is at 2 seconds from the collision, and you can see the spread of the other vehicles there under different crash scenarios. Another second later, note the scale's halved now, we can see the proximity of these vehicles relative to the vehicle with the sensors in it. And we can see that the vehicle stands no chance with the current AEB sensors to detect vehicles coming from right angle and to the side. So that's where the technology and this sensor has a particular limitation. And there's actually a whole range of crashes where it becomes very difficult for the vehicle not to have a false positive. So if you're passing another vehicle, to recognise that that's a head-on that's going to occur is actually very challenging. And compromises are going to be needed in determining how we implement this technology. So we've looked at some theoretical models and a sort of framework to look at assessing the capacity and the potential of all these technologies to help us. And we can have a sort of effect here where we have a full effect, where there's full braking and the crash is avoided altogether. Some mitigation where there's some braking but there's still an impact that occurs. And a situation where there's no effect at all, where the vehicle doesn't even react. Now for the current suite of technologies, when we map that out using some diverse assumptions, we can see that this is the sort of distribution we get. So we can see that quite a lot of the incidents, and this is from real-world data we've investigated, crashes we've investigated, we can see quite a lot actually don't have any effect where the vehicle would have reacted. Quite a lot are in this mitigation scenario where there is some braking and there will be some assistance to the crash consequence. Very few fall on this category of avoidance. In the future, if we could have vehicles that instantly recognised a threat and responded, this would be what we're dealing with if we zoom in on that part of the curve. And that's where the potential of machine learning and these certainly can come in. What we need is sensor fusion, where we need the feedback from a range of sensors determining what the situation is and the vehicle to make intelligent decisions around how it's going to respond to that situation. But it's got to take input from various sensors, and one of the great challenges we have at the moment is if there's smoke or fog, the vehicle can't see forward. So you can't rely on the visual detection, you've got to rely on other means there. So what I'll just say is, what does the future hold? It will indeed be a very brave person to predict how it will roll out. I'm more than confident the technical capability will be there, but there's many things that will shape how society embraces these technologies. There's the aspect of insurance alone. There's regulation, litigation, community acceptance of the technology and how they'll interact, the human-machine interface, and of course politics can play a role in all of that as well. The future mobility agenda is really shaping up in an interesting way, and I think we're going to rethink the use of space in our cities and how we prioritise movement. But the key message I'll leave with you is a consideration of, are we focusing enough on the transition? Are we putting enough attention to optimise our transition across to that utopia that may exist? Thank you.
Thanks, Jeremy. So the next speaker is Ian Reid. He is a laureate fellow and the deputy director of the Australian Centre for Robotic Vision and a member of the Australian Institute for Machine Learning.
Thanks very much, Anton. So, in common with a lot of the people at the Australian Institute of Machine Learning, I'm interested in how to make computers see. Computer vision is the subject that you see there in the centre. I've put it in the centre because that's the field that I'm in. But it really draws on a whole bunch of different areas from mathematics and computer graphics, optimisation, probability and so forth. And increasingly, it's drawn on machine learning. And in fact, a lot of the great advances in machine learning over the last decade have been either influenced by computer vision or driven by computer vision. And hopefully I'll be able to give you a sense of that. In general, computer vision is the study of the mathematics and algorithms processing both images and video to infer scene knowledge and understanding. And if we take computer vision into what we might call robotic vision, it's to enable robotic interaction. It's not just an end in itself, but it's to understand the world so that a machine can interact in some manner that we might deem intelligently. So why would we be interested in putting cameras on robots? Why do visual sensing for robots? Robots have been in factories for many, many years, but those robots in factories that were part of a mini-industrial revolution in, say, the 1970s are blind. You can program them to do different things, which is why they're great, but they can't sense their environment. And that's one of the reasons that you haven't seen robots penetrating beyond those very controlled environments. If a robot or a machine, an autonomous system, is going to operate in a dynamic and uncertain environment, it's got to be able to perceive its environment. It has to sense and understand that environment. It's not just enough to have a sensor. You need to process that sensed information into something that can be used to act in some sensible way. So that's why I'm using the word perceive there. And there are a whole bunch of advantages for doing that with cameras. Obviously, there are other sensors around, and perhaps in the forum we can talk about some of those other sensors. My particular interest has been for many years in cameras. And there's a whole bunch of reasons why cameras are potentially very useful sensors for robots. They're inexpensive these days, lots of them. I guess there are 500 cameras or more in this room. Every one of you is probably holding one in your hands. They convey a vast amount of information about the world in real time. Video has a huge amount of stuff, and they're passive. So you don't have to emit any radiation, you don't have to throw laser light out into the world, you don't have to throw sound out into the world. You are really just absorbing the ambient light in the world. And because of that, or one of the reasons that leads to, is that they have very low power consumption. So you can put them on drones, for instance. So they promise this flexibility. I don't think it's an accident that we live in a visual world and we operate this way. Furthermore, we've engineered the world because that's the way we operate. We have road signs that try as you might with your LiDAR system that can tell you how far away every point in the world is. It tells you what the geometry of the world is. It can't tell you what's written on the road sign, whereas a camera can tell you potentially what's written on the road sign. There's a whole bunch of problems. I started out by talking about what computer vision was and how it relates to machine learning. Computer vision, robotics, artificial intelligence, all of these things started out around about the 1950s together in a few key labs around the world, and they've gone their separate ways. And one of the reasons is that computer vision was unable to deliver on its promise for many, many years. And part of the reason for that is that images and video contain a vast amount of data, but much of it's redundant. And we didn't really understand how we can take that vast array of pixels, so megabytes of data per second, and turn it into something actually meaningful. Part of the reason for that is that in a standard camera, you lose information from the 3D world down to a 2D projection. Humans are incredibly good at inverting that projection. Even with one eye closed or just looking at a 2D image, we're able to understand how far away things are and interpret those images without necessarily having recourse to any kind of depth sensor. But information is lost, and we need ways of inverting that perspective projection. We also don't really understand how the human visual system works. And one of the early thoughts in artificial intelligence, one of the early labs, particularly the AI lab at MIT, were very interested in the nexus between psychology and neurophysiology and understanding how the human visual system worked. And there was a thought that all we've got to do is understand how the human visual system works, and then we can replicate it on a computer. Of course, that was doomed to fail. There were some other attempts, and there are some very promising research directions that are bio-inspired, that you look at biology and try to replicate that. So I don't want to knock that, but most of my career and most of my colleagues in AI/ML take a more pragmatic engineering approach. It's not that we're trying to replicate how a system works, how a biological system works, but we would like to replicate the functionality of the system. We don't really care whether it's bio-inspired or not. And this last point that I've got here is really important, and it gets to the heart of the power of machine learning, that we don't really understand how to represent or use prior knowledge. And that's why humans are so incredibly good at using a sense of sight. We're leveraging an incredible amount of knowledge that has been learnt over decades in the case of most of the people in this room, millennia in the case of the evolution, or in the case of the evolution of the species. we haven't really understood how to represent or use that prior knowledge. And I guess the big breakthrough in computer vision has been the advent of deep learning and the fact that you can now distill a huge amount of prior information just by showing lots and lots of examples to an algorithm, rather than trying to hard code your face recognition system or your face detection system or your cat versus dog detector. You show a generic program lots and lots of examples, and that turns out to be an incredibly powerful tool. Robotic vision is potentially transformative. If you could sense the world and understand the world around you as an autonomous system, you could go into a whole bunch of places that you can't currently go because you would get stuck. And the one that we've talked about already a fair bit this evening is self-driving cars. If you can sense the dynamic environment of an urban landscape, then your car can actually go out and hopefully not hit people and drive around roads and so forth. But there are a whole bunch of other things, some of which are of particular importance to Australia. Autonomous infrastructure and environmental inspection. Australia is a vast country with very limited personnel to look at the vast infrastructure that we have. Some of it's in very remote and inhospitable places like under the sea or in the middle of the desert and so forth. Robotic assisted and collaborative manufacturing is an area that is going to be huge, and it would give the ability for a person to have force multiplication. A person controlling a fleet of robots to undertake some task in manufacturing, for instance. Logistics and fulfillment, last mile delivery and so forth. I'll talk a little bit about that in a second in the context of some work that we've been doing here at University of Adelaide. And robots in construction might be a stretch goal, if you like. Very unstructured environment, much less structured than an urban driving example. But they would love to be able to take robots into those situations, because then they would pull out a lot of the danger factor. Costs construction companies millions and millions per year in safety audits and deaths of people in construction. I'm sure there was another example. Agriculture, another great example. Workforce in the average age of farmers in Australia is over 60 now. Where are the people going to come from to maintain that industry? It's almost certainly going to have to come from people with robot helpers. But to go into that environment, you need to be able to sense the environment. So we put together at University of Adelaide and with collaborators around Australia a Centre of Excellence in robotic vision. It's been funded for 7 years to develop technologies that enable machines to sense, understand and interact with complex real-world environments. And our expertise here in Adelaide, I'm one of the investigators, Anton is another of the investigators, in fact of the 70 or so people in AIML, depending on how you define robot vision, depending on how you define involvement with the centre, as many as 25 or 30 of those people are involved in this Centre of Excellence in robotic vision. And we're partnered by Queensland University of Technology, ANU and Monash, and a number of eminent international organisations as well. Our specialty here is in visual perception and scene understanding. So I thought perhaps that could be my segue into showing you some of the stuff that we do that's relevant to things that have been talked about already. So for example, driverless car technologies. What is the research that we do here in Adelaide? I've already said images and video encode a huge amount of information about a scene. How do we get that information out? So a couple of examples. Visual navigation and mapping is an area that we've worked on for many years. How do we extract the scene geometry just from a camera moving through an environment, and can we localise ourselves with respect to the geometry that we've extracted? Can we go beyond that to understand the scene? Not only say what is its geometry, but detect people, detect pedestrians and so forth. Can we read traffic signs and so forth? Can we identify where the road surface is, where the pavement is, where traffic lights are, and so forth? So here's an example of work that has been going on in our group for many, many years. The idea that you can move a camera. This is a single camera. I've sped it up 60 times. This is actually driving in real time around a block somewhere in the Adelaide CBD. And these points are the geometry of the scene. The blue bits that you're seeing there are where the camera is. And it comes around the corner, it comes back to somewhere that it's been before, recognises that it's been there before, and then snaps the map that it's building of its environment back together. This is a really important technology for cars. You need to know where you are. GPS is not a panacea. Drive down Grenfell Street, and as the map tech guys will tell you, suddenly your GPS is all over the place. So you need to be able to know where you are. Cameras can deliver that kind of capability. Does anyone here have a Dyson 360i vacuum cleaner? No, I guess not. Exactly the same, or almost exactly the same technology is in some of the high-end robot vacuum cleaners. The Dyson 360i is an example. Far too expensive for me to own one, unfortunately, much as I would like one. I talked about scene understanding. So this is an example of classifying every pixel in an image or video stream. So what you're seeing here is the video is being presented, in this case to a deep neural network, which is telling us what is the class of each pixel, what does it belong to. So here you're seeing this purpley colour is road, the dark red is a bicycle, the light red is a pedestrian, yellow is a street sign, somewhere you'll see some orange ones, they are traffic lights, red is pedestrian, blue is another car, green vegetation, grey is buildings, pink is pavement. These are really important things for your self-driving car to know. And one of the reasons that you've seen significant strides in self-driving cars recently is the advent of deep learning able to do this kind of thing. So this is an algorithm that was developed at AIML, and currently it or its cousins are amongst the best performing algorithms in the world. You can do other things. If you can segment a scene into its constituent parts, then you can recognise objects and where they are. So what you're seeing here, we've done the same thing with a bunch of objects. We've shown a deep neural network a number of examples of these objects, and so it can now tell us which object is which. It can segment out the human hand from the pig, from the whatever. These are particularly easy examples because they're nice and brightly coloured, but hopefully you get the idea. And if you can do that, then you can start to do things like picking up objects. So you can say, pick up the pig and put it in the pig place. Pick up the, I can't remember what's next. The reason why I'm showing you this is to show you some of the other work that we've been doing. I mentioned that I was going to talk about fulfillment and logistics. So as part of the integrative effort of the Centre of Excellence in Robotic Vision, we took this perception idea together with our colleagues at Queensland University of Technology and built a system to enter into something called the Amazon Robotics Challenge. So I'll just talk while this is running. So Amazon, for those who don't know, is the world's biggest owner and user of mobile robots. And they are, since they acquired Kiva, and who are a logistics fulfillment company, and they've expanded that operation. But their mobile robots are dumb. What their mobile robots do is that they move around a fulfillment warehouse and pick up a shelf that has the right products on it, and transport that shelf over to a person who is sitting there who picks the right items off the shelf and puts them into boxes or puts them into envelopes and so forth. The pain point for Amazon was having a human in the loop, needing a human in the loop there. And so they posed this challenge, and for each of the last 3 years they've run, it was originally called the Amazon Picking Challenge, then it was called the Amazon Robotics Challenge last year. And the idea is to design and build a complete robotic system, so involving perception and actuation and so forth, to pick out a bunch of items from a tote. So these are items that have been supplied by Amazon, and you have to recognise all of those items, pull them out and put them into a particular place. So we put together a team of researchers from University of Adelaide and from QUT. They did most of the mechanical and mechatronic work. We did the perception, got our team together, flew them up to Japan where they reassembled the robot that had been built and won that competition against a number of international groups, including a few companies, including a group from MIT, Princeton, and so forth. And what you can see here, this is the view of the camera up here. It looks down, it tries to identify particular objects. Oh, and I've run out of video. So given that I've run out of video, perhaps that is a sensible place for me to stop. Thank you.
Fantastic. All right. So, Ian's being a bit modest there. That result of winning the Amazon challenge was they took the robot up there in their hand luggage. It was made out of what looks like old bicycle parts, and beat companies that had budgets that were literally 100 times greater, and they did it with better sensing and better calculation. It's a fantastic result. Okay, so now we have a panel session. Hopefully you've brought a lot of questions with you. I've got a couple of my own. I invite the panelists to come and sit up here and we'll give it a crack. Okay, so my first question is, when can I have a driverless car? And particularly, I want one where I can read a book or, watch a movie, or actually go to sleep would be even better, while it drives me to work.
Okay, so again, often it's the humans that are the issue. So already we're seeing humans do some really interesting things, just thinking about your question, including one person who unfortunately met his demise by stuffing an orange into the steering wheel so that he didn't have to hold it. So there's all sorts of things that, again, it's emergent behaviour by humans. It's one thing to have technology that works. It's another thing to have humans who decide that they're going to get round it or do other things. And I think, and I can certainly be corrected because this is my area of expertise, but one of the interesting issues is how much autonomy do you give humans? Because again, we've got this catch-22 of, in some ways, it's really dangerous to not to give them any control, because they often take the control back when they're under stress, which means we make dumb decisions because cortisol changes all sorts of things in our brains, and stress does a number of things to us. But if we don't give that capacity, then again, if the person in the first place has done something which means that the car is going to get into a situation where it has to do something it can't necessarily do. So one of the last crashes was getting into a situation where the car actually crashed because, as you said, the difference between head-on and something in front of you is really difficult for AI to figure out. That it means that, again, human beings are very often the issue. So most of it is trying to orchestrate our capacity for doing really stupid things into the process.
Yes, and I fully concur with those views. And one of the challenges, I think, for society, if you look at the whole premise of the legal system, is catering for those extreme elements, people who do silly things. But I suggest that as system designers, system operators, we do have a duty of care, even to those people who take high risks and aberrant behaviour and so on. We have a duty of care because we can predict those sort of behaviours are going to happen. It's interesting when you look at parallels in aviation, that much of the training, the simulator exercises, everything in aviation is all about when to take control back from the aircraft. And that famous adage, the famous last words before a crash is, what's it doing now? And very much it's about, understanding the complex systems and knowing when you have to interact and appreciating that you're often under duress when you have to interact. So it's about breaking the problems in those stressful situations down into bite-sized chunks so you can deal with it. Now, I think the key answer then to the question is what sort of appetite we have around that. What's the training regime? How much control? Under what circumstances we allow the humans to interact? And we can have the full spectrum of that. And I also believe we will get to fully autonomous systems in the future, but in very controlled, specific environments. But I don't think it'll be the sort of free-for-all Jetson thing that the utopia we're being painted at the moment.
So let me I'm not going to disagree strongly, but I do want to make the point that pretty much technologically we are already there. You could, in theory, have your Tesla drive itself pretty much under just the control of its sensors tomorrow if you wanted. But as the others have pointed out, there's a whole bunch of reasons why that might not be a good idea in the first instance. And what I actually think is almost certainly going to happen in the first instance is that there will be areas where we don't try to manage a transition between humans and machines interacting, but we actually say, this is an area where it can only be machines. So the example that's being used in the States is that they might close off a section of central Las Vegas and it become just open to Uber or Zoox or whichever company manages to get a contract to ferry people around under some kind of autonomy. Maybe in time we'll see a move to a more general free-for-all, if you like. I suspect it's going to be sooner than Jeremy thinks. And probably it will be driven by the imperative to save lives. The fact that maybe there's another point to make along the way, which is that a number of companies, they stratify self-driving cars in terms of level of autonomy given. And one of the most difficult things is managing the handover of control between an autonomous system and a human. And how do you transition that in a dangerous situation? It's almost certainly safer just to let the autonomous system that has detected the threat in the first place take the evasive action. It can see all the way around the car. It knows exactly how fast the car is moving and so forth. The real question about that is the legal framework and who ultimately would be responsible. But for that reason, there are a number of manufacturers who are going straight for what they call level 5 autonomy. So no human in the loop at all.
Yeah. Okay, so audience questions. The first person to put their hand up was this boy here, and I'm desperate to hear what you've got to say. Tell me. The question was, how was the first line of code made? Yes, indeed. Well, so there's a fantastic history of coding, and one of the first people to ever write a program was a woman called Ada Lovelace, and she, I think, was the daughter of Lord Byron, who was a poet, and her mother was so desperate that she not become a poet that she taught her to become a mathematician, and she wrote computer programs before there were computers. How about that? My daughter, I think, is up the back here somewhere, but I've had another question from a kid up the front here. What's your question, mate? No, sorry. No, the child behind you. I'm sorry. I promise you're next. Fantastic. The question was, if we have robot butlers, will we have an app to control them, or will the government control them? I think that's a wonderful question, and I think my answer is that there'd be a bit of both, but I'm going to let Fiona decide because she works on that more than I do.
It is a great question. So one of the things that we're looking at in Finland on the steering committee for what the artificial intelligence program will actually look like is exactly those sort of questions. And in what circumstances can you use your own app, and in what circumstances do you need other people to be able to take over and use that machine? And some of the issues around that are things like trust in traded information, what you can actually see, who else can see the information, what they can do with it. Different countries have completely different ideas on that. We cannot get alignment. So again, it's not so much the technical issues, it's the fact that what we actually need is alignment across different countries and nations globally on agreements around things like that. And we're shocking, we can't agree on any of those things. So that's the short answer, is it's being looked at, and it does depend, but it's a very curly problem.
Fantastic. Sorry, I bumped you twice there. Now you've got to have a question. Yeah.
I feel embarrassed now. This might be directed towards Fiona as well, I think. The society and its interaction with robots, intelligence, whatever, There's been a story recently about the Amazon Alexa, which started randomly laughing in the middle of the night. Is that possibly someone's attempt to try and make these machines more personal?
Seemingly, yes, it was, and they were trying to think about different types of laughing, so it just sounds creepy. But the issues, I guess it's the layering issue. So there's a lot of discussions. So just having come back from there's a lot of discussions around what Alexa can hear. The stuff about is it listening? Now that there's screens, is it watching? And so it's really interesting the variety of comfort people have with having something in their home that potentially, yes, can monitor, but your mobile phone can monitor you too. So it's really a decision around what do we want those things to do, and how much do we trade convenience for having something there that can potentially monitor you. But yes, there's a lot of debate and discussion on whether it's a female voice, whether it does laugh, whether it does get involved, what that means, and that creeps a little bit into that kind of whole anthropomorphisation area as well, of getting you more comfortable. The more you're comfortable, the more you will actually utilise it. Certainly for Amazon, the more you'll buy things off Amazon. And so, yeah, depends on which angle you look at, whether it's a marketing angle, a comfort angle, a convenience angle, a security angle. They all take ages to discuss.
And while you think of another question, one of the things that's taking place is that, there's a huge first mover advantage in machine learning. So a large part of the value in any machine learning process is getting the data in the first place. Right? You need to have training data that you have to capture in order to learn anything from. One of the great advantages that Amazon have in creating Alexa is that they're out there in people's homes capturing all that data. It's a big part of the reason why those systems are cheap. The Google Home and the Alexa systems are quite cheap, and they're subsidised out of Google and Amazon's interest in capturing data in your house, so they can use that in order to train better systems in the future. It's the advantage that Tesla have over all of the other driverless car companies. Google are going around very slowly, scanning the world with a laser scanner. Tesla are out there capturing thousands and thousands of hours of footage of real roads and real traffic incidents all day, every day, out of their cars. There's a huge first mover advantage. Sorry, somebody up the corridor here.
I was just wondering, do the cars recognise the rules of the road, and who gives way to whom, and the speed limits, etc.?
Yeah, there's some great questions. So if your driverless car, it has to obey the road rules, but there's a whole lot of other ambiguities about driving on the road. And if you pay more, so at the moment, if you pay for a faster car, you can accelerate more quickly, right? If there's driverless cars, you could opt for an option that says, I want you to be more aggressive. What happens if you're, it would be very tempting if you see a driverless car coming along to jump out in front of it and see what happens, right? There's all sorts of fantastic problems, but I'm sure that Jeremy's got more sensible suggestions than mine.
I mean, it's one of the things we'll have to pay attention to, and this is why I sort of ended with the focus on the transition, and that is, there was mention of infrastructure as well here. The cars need to be able to read the roads, we need to do the best we can to allow them to perform at their peak as well. And already, with some of the sensors and that, we've had cars misinterpret 80 signs on freeways and slow to 30. And things like this. Now, these are unintended consequences, but we need to get on top of these things. And we need agile sort of policy making and laws and things to cope with the changing requirements over time. And what we're finding with some of the preliminary technologies now, so sort of the line marking matters, the quality of the road signs matters, and the Europeans brought all their vehicles out to Australia, and some of the manufacturers threw their hands in the air because their cars couldn't cope with the range of signage we had here. So there are challenges around that, but the key is to be agile and keep responding to the situation. But the road rules is an interesting one. I mean, you know, we all, if I put you all at an intersection and you were picking gaps in traffic and trying to turn out of a side street, you'd all accept different gaps, basically. There'd be a distribution around that. What do we program in autonomous cars, and how fine do we cut that? So it's going to be fascinating to see how that plays out.
One of the things that gets neglected, I think, by a lot of the manufacturers is the importance of social interaction. If you're going to have cars that are autonomously driven mixing with cars that are driven by people, which is a possibility, not for a while, but it is certainly a possibility, is that drivers make eye contact with other drivers. There's a tacit negotiation goes on. If there's steady filled traffic in front of you, then you'll catch someone's eye, or they'll lift a finger or something like that, and you're able to drive out. They're very subtle things. And I tell this in the context of having been to India about a year and a half ago, and we were driving one of the scariest drives of my life. I wasn't driving, someone else was driving, but we reached the outskirts of a fairly big city, and it was getting dark, and there were 4 lanes of traffic, very heavy traffic going in one direction, 4 lanes going in another, and then there were 8 lanes crossing. And all of a sudden, the driver stopped, and I wondered why on earth he'd stopped. And I looked over, and in the middle of the intersection, barely visible, was a policeman who'd just done that. And so I spoke to some of my Indian colleagues. It was a computer vision conference, and they were all trying to build self-driving cars for India, and I spoke to them afterwards and said, good luck seeing that for the time being. But there is most definitely a need to do that kind of social interaction. The other example is knowing that a pedestrian has seen you. If a pedestrian has looked in your direction, there's a good chance that they have seen you. You potentially behave very differently from if they haven't seen you. They're approaching a crosswalk. If they've looked in your direction, you know that there's a reasonable chance they're going to stop. Unless perhaps they know that you're a self-driving car and they want to see what's going to happen.
And they jump in front of you. Yeah, that's pretty well what I was going to say as well. And one of the other things that we notice is, if you look at it in terms of systems, complex systems, even when you cross over that 4-way crossing even, you notice that people are able to weave because we just use that capacity so well. And if you try and put rules on that, we bump into each other and we stop. So the levels of complexity in a self-organising system are also something that you bring into account with that. And when you combine that with, again, human nature and the fact that we will get some twits that will jump in front of a car, then it just becomes really interesting.
Fantastic. We've got time for one more quick question, and I'm going to volunteer to answer this guy's second question privately afterwards. But somebody else?
I was just interested, you've talked a lot about cars replicating what we do with a car at the moment, is that the car itself has a degree of autonomy. Where do you see the role of other sensors, particularly cars themselves carrying sensors so that they can sense through a non-vision system? So sensors on roads that have information, sensors in other cars that might have information. Will that have a role in this new autonomy type environment?
Absolutely. Yeah. So I guess you can break those down into sensors that are on the car, that are giving the car individually a level of autonomy, and then the infrastructure that's enabling things like inter-car communication, so that you could get convoying behaviours, increased traffic throughput, for instance. You could imagine a system where you can only enter the CBD if you switch on full autonomy, and that involves inter-vehicle communication, so that the arbitration is then done by a central controller rather than by you, and that would It might mean that you're slightly slower to get to work, but it would mean that everyone else, on average, got to work much faster. So certainly that there's a role for that. There's a company based in Adelaide called Coda Wireless, who's one of the world's leading suppliers and developers of inter-car communications. I suspect Jeremy knows a lot more about them than I do.
Fantastic.
And look, sorry, we also did an integrated study with Coda Wireless, and the real potential of autonomous vehicles is connectivity. The fact that they can speak with other vehicles, the fact they can speak to infrastructure, and where the sensors might fall short or be deficient, then that communication can make up for it. So I guess the question, or one of the aspects to your question, is sort of the rollout of redundant systems, and what level of fail-safe safety we might aspire to, I suppose, and the economics around that.
Fantastic. Thank you very much for your questions. Thank you, panel. I'll pass over to Mike to wrap up.
Thank you, Anton. And could you please join me in thanking Fiona, Jeremy, Ian, and Anton. Thank you so much. And I have a small gift which I'll present very shortly. Can I also thank you all for coming out this evening? It's been wonderful to see you here. Our next Research Tuesday's presentation will be held on the 10th of April, right in the middle of the Commonwealth Games. And it will be entitled Engineering Champions, and we'll look at the incredible performance advances being achieved in the field of sports engineering, including, of course, right here at the University of Adelaide. So I hope to see you there. Thank you so much for coming this evening. All the best.